Hello everyone and welcome back to the Solana Auditors Bootcamp. Just a reminder, my name is Andre and I'm a lecturer during this course. This is the lesson number 4 of this bootcamp, and this lesson is going to be about fuzzing with Trident, but this time part 2. So we will talk about some additional features that are possible with Trident. So let's just jump in. On the screen, you can see the agenda of this lesson, but firstly, I would like to tell you that the part 1 was actually about fuzzing, an introduction into fuzzing. I told you, or I described what fuzzing is, what is the Trident, how the underlying random data looks like. This lesson is more about the additional features, or I would say extra features that are possible with fuzzing. But yeah, most of them can be also applied to the, let's say, introduction part of fuzzing, as these are really good features to improve your fuzzing experience. So firstly, we will talk about the invariant checks. In the previous lesson, we discovered basic panic, or in general, it was subtraction with overflow or division by 0. But on the other hand, you can also define invariant checks within your fuzz tests. And these invariant checks are great for in comparing accounts before the instruction and after the instruction invocation. So you can check if the accounts were updated as expected. Then you can also specify the instruction sequences within your fuzz tests. You can also specify the custom error handler, so you can check if the correct error was returned based on the, let's say, instruction data, input data. You can also specify, I call it well-structured data. You will see what this means, but you can, I was already referring to this as kind of customization of instruction input data. Then there are available client methods that are also great for customization. So you can, before actually fuzzing, you can, for example, add custom accounts to the fuzzing environment, such as, for example, configs and so on. Then we will talk briefly about the Trident Manifest, which features I think are great to turn on or modify within the Trident TOML file. Then we have point about features that are currently in development, so you can look forward to those. And then the last point is about in-code examples. So what I will talk about, I will show you in examples in code. The last thing from the agenda, or the reminder maybe, is the QR code that leads to the Trident docs. So if you would like to know anything about the Trident, how to install Trident, or maybe where to find the examples, you can check the GitHub obviously, but we have also Trident documentation. So that's everything from the agenda, and we can go to the invariant checks. This can be particularly helpful when you want to compare account contents before and after the instruction invocation. That means not only you can discover panics within your Solana program, but let's say your program also transfers tokens, for example, and you would like to compare if this transfer was performed as expected. This means you can define invariant check after each instruction you will see in the in-code examples, which will be called after each successful invocation of that instruction. So let's say you have update instruction or transfer instruction, and if this instruction invocation was successful, then you can, or the Trident will call the check function, which is defined by you as a developer. And within this check function, you can compare the accounts that were involved in the instruction, and let's say the accounts were mutable. So you can compare the contents of the accounts before and after the instruction. So you can see if the behavior during the instruction was as expected. In this case, this can be particularly helpful, for example, for changes in account balances. So you can check if the account balance changed as expected. The second thing is again the QR code. We have already prepared the example to show you the invariant checks. The invariant checks are contained within the multiple examples, but this QR code can or will lead you to one of them. So feel free to check, but I will show you how to specify invariant checks also in the in-code examples. The second feature is instruction sequences. Currently, in the previous part, we were working with completely random instruction sequences. So let's say your Solana program contains 5 instructions. Then the instruction sequence, when not defined, is completely random. So if you need initialization before some other instructions can be called, this was not ensured, and let's say the 5th or 3rd instruction from the sequence that should be called was basically called. So in this case, instead of calling the initialization first, the update was called first. On the other hand, with the Trident, you can specify the instruction sequences. So again, if you need to firstly initialize the accounts for fuzzing, or let's say data accounts, and then call update or swap or whatever other functions or instructions, you can actually define desired sequences of instructions. These are actually split into 3 functions, so you can specify pre-instructions, instructions, and post-instructions. Again, these are all used in most of the examples, so you can check the examples, but we will go through more in details in the in-code examples. This can be definitely and really helpful to define what instruction sequence you want to test. That's the first case. Also helpful when any kind of the initialization is required. So in the first case, you want to test a particular test case or test path, or let's say instruction path, with the random instruction inputs. So you can define these pre-instructions, instructions, and post-instructions. And even though the underlying data are random, these underlying data will be such random, so the instruction sequence you specified will be ensured. As I said, it can be also helpful when you need to initialize accounts before actually updating or calling other instructions. So in the pre-instructions, you can specify the initialize, and then you do not care with any other instructions anymore. This is the theoretical part within this feature, or for this feature, but as I said, more in details in the in-code examples. We can now talk about the custom error handler. As you can specify the invariant checks, you can also specify the custom error handler for each instruction. And for example, this can be helpful in 2 options. If you want to check expected behavior while returning errors. So the error handler contains the error returned from the instruction and also accounts, or the accounts sent to the instruction. and also the instruction data. And based on that, you can check that the instruction behavior or the return error is as expected based on the input data. The second option, let's say you expect some kind of instruction sequence, as we were talking previously, but you expect that one of these instructions will fail and return error. This would mean that the whole iteration would return, and the new iteration of instructions will be performed. Instead of that, you can specify the custom error handler for the instruction you expect that will fail, and this is something like you catch the error and return awk result. You can also check the returned error. So in the sequence of instructions, you can basically expect that, let's say, the middle instruction should actually fail. So this is from the custom error handler. Let's continue with the well-structured data. This is again one of the, let's say, more often used feature, which I called well-structured data. In this case, it allows you to customize, or it allows customization of data sent to the instructions using the arbitrary crate. So let's say you have some kind of instruction input data. And the second point of this example is, let's say the instruction input data are basically two unsigned 64 numbers. In short, we can say the first parameter is start time and the second parameter is end time, which are unsigned 64 bits long integers. We can refer to them as Unix timestamps. What is important in this example is it makes sense that the start time is going to be lower than the end time. So that's why the well-structured data or the customization using the arbitrary crate is actually important, because you can specify in the fuzz test, you will see in the examples, that the first parameter should be always lower than the second parameter. That means even though the honk fuzz or the underlying fuzzing engine will generate completely random data, it will, or the Trident will only accept data where the first parameter is lower than the second parameter, as you will see in the examples. And this can be particularly helpful, for example, for, as I was talking about, time intervals. So start at, which is the first parameter, needs to be actually smaller than end at, which is the second parameter. This is just the example. You can also define these kind of checks or rules for input parameters, for more parameters, or even the second parameter can be lower, or lower than the first parameter, and so on. We have prepared, I would say, I think 2 examples for the arbitrary customization, so you can check the QR code and see the example. Then we can continue into the client methods. So in this case, the client also contains some methods that can be really helpful if you would like to customize the environment actually before each fuzzing iteration. You can check the methods, you can see the documentation, and this can be particularly helpful, for example, if you want to add custom accounts to the environment. So let's say you want to add some kind of config to the environment, and for example, you are fuzzing smart contract or Solana program which does not have this kind of config. So you can manually, or you need to manually add the account to the fuzzing environment or before actually the fuzzing iteration starts. So you can do this basically with the with the methods that are available in the client. Now we can continue into the Trident Manifest, or we can call it, or it is called Trident.toml file. Within this file, you can customize actually a bunch of features, which allows you to customize the fuzzing session actually. Let's say those that I used most often are, for example, number of iterations. So in this case, you can specify 1000 of iterations. So the fuzzing session will end after the 1000 of iteration is hit. You can specify the fuzzing time. So this is not, or the fuzzing session is not limited with number of iterations, but the amount of time that it needs to pass before the end. It can be also specified that the session will end when the crash is found. So instead of discovering or finding multiple crashes, when the first crash is found, the fuzzing session will end. Then you can, for example, turn on the statistics. So you will see this can be really great because when the stats are turned off, you see that the fuzzing is running, but you do not know if the instructions are actually successfully invoked. So in that case, you can turn the stats on and you can see how many times the instructions were invoked, how many successful how many successful invocations there were, and so on. So these are examples from the Trident Manifest. Then we can talk about the features that are currently in development. So let's continue. There are currently a bunch of new features that we work on. Apart from that, we constantly are trying to improve the user experience and the fuzzer experience with maintenance of the Trident. These are on the slide basically bigger features that we would like to implement within the Trident. The first one is something called Light Client. So currently we are using the program test crate, which is great, but there is kind of overhead that is not required for, let's say, raw fuzzing. So in order to increase the speed of fuzzing, we would like to implement Light Client, which can drastically improve the performance of Trident into the hundreds or thousands of iterations per second, which we find it can be really helpful for developers and security researchers or auditors. The second thing we are trying to improve is less manual work. So as I was or as I showed you how to specify or how to initialize and write fuzz test in the first part, we would like to also implement logic that generates more stuff automatically instead of manual work that was presented in the first part. So we are constantly improving the automatically generated amount of code. Then we would like to also include new additional fuzzing statistics. Currently, we only support simple fuzzing statistics such that the successful invocations, number of instruction or number of invariant checks that failed, but we want to also include, let's say, compute unit statistics, for example, and so on. We are also looking into the multiple fuzzing engines, as this is kind of problem for the ARM users, especially for the Mac users, that they cannot run the Trident without the Docker, because the honk fuzz has problems with with Mac devices, so we would like to use different fuzzing engines that can be run on both or on all of the devices. Yeah, and currently, let's say it is already in master, and it is already a released feature, but this feature is not used by default. It is hidden after the config flag. It is support for derived macros. So as you could see in the part 1, the initialized initialized fuzzing templates contained 3 files, and the one file was actually account snapshots, and there were no manual work required from the developer perspective. So we think it might be helpful to reduce this overhead and to generate only 2 files. And instead of actually generating also the account snapshots file, you can derive it immediately in your Solana program, and it does not need to be generated within each fuzz test. The QR code leads to the developer branch. So for the latest, let's say, updates or implementations which are not yet released, you can check the developer branch, and yeah, you can have a look what is in the development process, what will be released. But reminder, these are more like experimental features, so it does not mean that when the features are in developed, if the features are in develop, they will be released, as we may find other possible improvements, or we may need to remove the features as we can find issues with the new experimental features within the develop. So that's from the in development features. Now, as we have the insights into possibilities or additional possibilities, extra possibilities of Trident, we can have in-code examples. So I will again, as within the part 1, share you my screen of VS Code, and I will comment everything mentioned here in the slides. So let's jump in. For the hands-on example, I have prepared a Solana project really similar to the previous one that was shared in the part 1 of the Fuzzing with Trident. So we can quickly go through the source code. You can see that I have already prepared the fuzz tests, so we will go through these. And just quick recap. So we were talking about the invariant checks, also the instruction sequences, also the custom error handler, well-structured data, client methods, which are really great for customization, and the Trident Manifest. So we will go through these 6 features that you can use during your fuzzing sessions. But firstly, let's talk about the implemented program. So our program has 3 functions, in this case initialize, update, and dummy. This dummy, functions, instructions. This dummy instruction actually does not perform anything, and it is here only to show you that actually the instruction sequences work, and if you specify instruction sequences correctly, then the unwanted instructions won't be actually called. In this case, we will specify that we do not want this dummy instruction to be invoked or called. We want to call only the initialize and update, so you will see how this behavior is actually handled or specified within the fuzz test. Then we can briefly go through the initialize and update instruction. So in this case, the initialize just set the fields of the asset account, and what is added here is this config authority, which is expected to be signer, and we have this config account here. You can see within the initialize context, within this context, that this account is expected to be already initialized. It is not mutable, and these are the seeds of the account. This is particularly helpful to show you how you can customize the fuzzing environment, or use the client methods to customize the environment, because we will actually manually insert this config and also this config authority into the fuzzing environment, so these two accounts can be actually used during the invocation of initialize instruction. We can continue, or we can go back to the entry point, and we can continue to the update instruction. In this case, the behavior is almost identical to the previous example. What is changed is this if statement that actually checks if the input 2 is greater than the magic number. If so, the invalid input number error is returned. Then I also added checked arithmetic for the subtraction and also division. And this is from my side also important to mention, that the fuzzer can actually discover errors or issues even when you have the checked arithmetic specified. Because, for example, this checked sub or also the checked div return none if the right hand side equals 0. In this case, checked sub, for example, returns none if overflow occurs. And what does that mean? That means it will call unwrap on none. That means this line will panic, or the program will panic on this line, and this can be catched by the fuzzer. So you can discover bugs, or your program can have issues or bugs even when you use checked arithmetic. So it is also great to use fuzzer if you are using checked arithmetic in your Solana programs. Okay, so I think I covered everything here. Maybe I can show you the contents of the config account that is stored in the config account I showed you within the initialize context. And the struct contains basically one field, which is authority, just to and the type is pubkey, just to show you the behavior of customization of the client. So I think now we can move to the fuzz tests. And first thing that I would like to talk about in this case are the instruction sequences. One point that I would like to also mention, which is not that important, but you can see that we no anymore include metaplex within the fuzzing environment. I just removed the metaplex cross-program invocation, and as I think it is not important to show you these features, so just to simplify the fuzz tests. But other than that, you can see the main function is pretty the same, and we can scroll up into this part. So what we have here? We have specified the fuzz data builder for my fuzz data. This is just Trident thing, so it is not important to describe you what is happening under the hood. What is important to describe you that you can specify pre-instructions, instructions, and post-instructions. This is apart from that, it is split into 3 instructions. It can be basically, or it behaves basically as not 3 instructions but 3 functions. It behaves basically as this was specified within the one function. What is important is that you can specify it, for example, just like this, you can specify only this pre-instructions function, and you can omit these 2. That would mean that you expect the initialize instruction to be called first and always first. And after that, you do not care what is called. So after that, it can be 2 calls to initialize instruction, 5, 10 calls, even dummy instruction can be called, even update instruction can be called even multiple times. If you specify it like this, that you specify for each function that you expect something or nothing as for the post instructions, that means in this case every iteration of fuzz test will contain only these 2 calls, in this case initialize and update. No more instruction calls will be performed during one iteration. So you can specify on one hand side let's say only the initialize instruction. So you just want to initialize environment, or not the environment, but you just want to initialize accounts, and you do not care what is after this initialize. Or you can specify particular instruction sequences this way, as we have specified in this example. So now if I clear my terminal output and run the fuzzing session again, we will wait for some time and we will see if we are able to find crashes. We found actually 2 crashes, which are basically one is unique, so these are identical crashes. I will stop the fuzzing session. And what is important here are these statistics. So apart from that, you can see that the initialize instruction was invoked 420 times. It was also 420 times invoked successfully. The update instruction was successfully invoked only 55 times. Apart from this, you can see that these stats does not contain dummy instruction. And that is, as I was talking about, we have specified that we want only this initialize instruction with the pre-instruction part, the update instruction within the middle part, and we do not want anything in the last post instructions part. So there are only these 2 calls in the every iteration. So let's say no calls to dummy instruction. So this is from the instruction sequences perspective. The second important thing is we actually found crashes. But I was talking about the program and I was talking about the update instruction, and as we are correctly checking that the input 2 cannot be higher or equal to magic number. So where do we actually found crash? We found crash, if we go back to fuzz instructions, we found crash in this invariant check. In this invariant check. This invariant check is specified as one of the methods of the update instruction. So apart from get data, get accounts, we also have invariant check. In this case, the invariant check is important if you want to check differences of accounts before the instruction invocation and after the instruction invocation. So these are basically the 2 parameters of the invariant checked function. And the last parameter is instruction data. So if the instruction data are important for you to check the differences, you can also use the instruction data within the function. In this case, I do not use instruction data. What I have specified here is I just take the account after the update instruction, in this case the asset account, and I take the counter field from the asset account. Then I subtract what was in the account prior to this update instruction invocation. So in this case it was 0, as it is initialized as 0. If no overflow occurs, so that's why I have match statement here. If no overflow occurs, I take the difference and I compare the difference. If the difference is higher than 5, I found an issue and I return custom error with number, let's say 5. This can be really helpful if, for example, let's say we found issues in the moonshot or the deck screener with the Trident. So if your Solana program is or has a lot of logic, for example, for trading or buying tokens, selling tokens, this can be really helpful when you would like to compare token balances before and after the instruction invocation and check if the balances were changed as expected based on the instruction input data. So that's why the invariant checks are really great. We can go back to the terminal, and now we can check the crash files. So I will just specify debug here. Sorry. And the path to the crash file. So Trident test. And crash file. Okay, so it will build the binary and we will see the results. Okay, we can see the results. So if we scroll up in this debug window, just quickly recap. So the first part in the output is actually the instruction sequence that was generated. As I was talking about this, we specified that we want to call only initialize and update. So you can see only initialize and update was created or generated. You can also see, for example, the input 1 and input 2 of the update instruction. And then the processing started. So firstly, the currently processing was the initialize. You can see the Solana logs here. You can check the output. You can also print something to the logs using the message macro within your Solana program and check it here just for, let's say, debugging purposes. And then the next instruction that was processed was the update, as I said, with these two numbers. Again, you can see the logs. What is really important here is this last part. This is pretty similar as for the part 1 of the fuzzing with Trident, where we could see actually the panic with, I'm not sure if it was overflow or division by 0, but we could see panic here in this section. But in this case, there is no panic message, but there is crash detected, custom check after the update instruction did not pass. And this is because custom fuzzing error with number 5 was actually returned. Origin is the update instruction, and this is basically as expected from this line. So this is the error that was actually returned. We found such numbers that the update resulted in difference higher than 5, so we returned error. So this is, I would say, all from the invariant checks. For more informations, just you can ping me on Discord and we can discuss things, or you can also check the examples on our Discord and you can see possible variants that can be specified within the invariant checks. So yeah, we were talking about the instruction sequences, we were talking about the invariant checks. Right now I would like to talk about the customization, then we will talk about the well-structured data, then about the custom error handler, and lastly about the manifest. So let's go to the customization with the client methods. I was talking about the initialize instruction, and this instruction contains two additional accounts, which are config authority and config. And the Solana program does not provide logic to initialize this config account. This config authority is pretty simple, as this is signer, so it can be basic key pair. But how can we create actually this config account that is owned by our Solana program that has this PDA. So let's go back to the fuzz instructions. This is expected, the account is expected in the initialize instruction. So within the getAccounts function, we can start with this logic. Firstly, we called setAccount client method with the whatever number of lamports you want. This is something like airdrop. What is happening under the hood is that this method generates random key pair, stores it within the fuzzing environment, and the account is additionally initialized with this number of lamports or Solana, in this case 10 Solana. That means you do not need to perform any additional airdrops and so on. The second thing, we use try find program address, which is defined for the pub key, and we know from the Solana program what are the seeds for the PDA of the config account. In this case, it is static string config and the pub key of the config authority stored within the config account. As you know, last part of the seeds is the program ID of the program that owns the PDA, so you specify your program ID here. This will result in the config address and config bump. The next thing is you specify actually the config account. As I showed you, the config contains one field which is authority of type pubkey. So you specify the config account and you specify the config authority which was used within the PDA and was also previously generated. I think I forgot to mention that this setAccount method actually returns the freshly generated key pair. You can see it here, that the config authority is actually key pair. So we store the pub key of this authority here within the authority field of the config struct. Then we need to serialize this config struct into the byte array. If you expand using the anchor expand command your Solana program, this try serialize function is actually generated by one of the macros of anchor, so you can freely use it. And you can see the first thing you need to specify mutable byte array, and the second thing you can call the try serialize method that is defined for the config account specified within your program, and you just input the mutable reference to the freshly initialized byte array. Under the hood, this try serialize method or function actually takes the discriminator of the config account, inputs it into the byte array, and then after these 8 bytes of discriminator, it appends contents of the config struct. So basically common behavior of storing structs within the data accounts using the anchor framework. Then you have basically everything to create custom account. So you can again take client and call function or method called setAccountCustom, and in this case this method takes 2 parameters: address, which is reference to public key, so this is the address of account you are about to create, and account shared data. So what's the address? So the address is obviously the PDA we just derived here a few lines before on the line 58, or sorry, 88. And then the second parameter is account share data, which actually contains create method, and within this create method you can specify number of lamports, so this is not that important as you are manually setting the account, so you can specify whatever number you want. So in this case I have specified 10 Solana. Then you use the byte array we just serialize the config account into. Then we set the owner, which is obviously your Solana program. This account is not going to be executable, and it is we can set the rand epoch to 0. It is not important to set it to different numbers. As you could see, we were actually able to run the fuzz tests. Unfortunately, it will build the fuzz test again, so we need to wait. But there I did not make any changes to the source code of the fuzz test, and you could see previously that we were able to actually run the fuzz tests and even find crash files. So this means this manual customization of client using the client methods actually works correctly, and you can set up accounts this way if you would like to, that are not possible to be created using any instructions within your Solana programs. So this is still building, so we will wait for some time and I will get back. Okay, fuzzing started, and you can see it ran for, let's say, 100 iterations, and it already found crash, but I can stop the fuzzing session, and you can see that the update and also initialize was successfully invoked for some number of iterations, in this case 267 and 31. So we are sure that actually the customization or the manual setup of the account works correctly. We do not need to check the crash files, as we already checked these within the previous parts regarding the invariant checks and instruction sequences, so not important right now. The second thing, or the next thing, not second, the next thing that I would like to talk about is the well-structured data. So you already maybe noticed that we are using arbitrary crate. This crate is actually really helpful because it can help you to tell the fuzzer which random data accept and which random data not accept. Just maybe note, it is also used here. So in the instruction sequences, you tell the fuzzer, I want to fuzz these instruction sequences. So instead of the underlying data are still generated randomly, but you are setting limits with the arbitrary so that these functions try to deserialize from the random data these initialize and update instructions. If it's not possible, then the iteration is skipped. If it's possible, the iteration is actually executed. In this sense, the iteration means initialize and update the instructions second after the first. Okay, so well-structured data. We can scroll up, for example, in this update instruction data. As these are only two fields that are actually passed to the instructions within our Solana program, so we can use the customization or customization here. I will uncomment this code, and in this case I have set it for the range 210 till the 215, but let's decrease the range to 11. What this line actually specifies? This line specifies that the input 2 is accepted only from this range. So the honk fuzz, the fuzzing engine that generates the random data, still generates the random data, but your fuzz test only expects numbers from this range. So everything else is not important for the fuzz test or for the fuzzing session and is skipped, but these numbers for input 2 are important for your fuzz test and will be executed in the update instruction. So we can actually, let me first remove the crash file. So we will refresh the crash file. I have this specified, and let me run the fuzzing again. Firstly, I will clear the terminal, and let me run the fuzzing again. Again, it has to be built, so we will skip this. Okay, fuzzer just started running, but I need to terminate the fuzzing session, as these numbers are really small, so it won't trigger actually the difference higher than 5. But we can specify it, for example, for 200, let's say 40 and 240 again, so this will accept only 240 in this case. So let me clear again the console and run the fuzz test again. The fuzzing session just started, and you can see we already found an issues, in this case 9, 10, 11. So I will again terminate the fuzzing, and we can again call the debug. Okay, let me Trident fuzz run debug fuzz 0 Trident tests, fuzz tests, fuzzing, workspace, and the crash file. So we can see the outputs. Maybe I can comment on what was the mistake. The range was pretty small, and it could result it only in the numbers 210 and 211. And if you input the numbers here, so 254 subtracted 211, it is something 40 something, and after the division it would be, I think, not strictly higher than 5, so it can reach maximal number of 5 something, so it won't be able to find an issue specifying these numbers. But let's go back to the debug window. Yeah, we can see that the input 2 is exactly 240. I can show you as we specified here within this, I'm referring to this as well structured data within this arbitrary macro. And then again, the custom fuzzing error 5 was returned from the invariant check of update instruction. So using this, you can specify a lot of scenarios of limiting or specifying boundaries for numbers during the lesson. During the slides, I was referring to example where you have input, first input of the instruction is, let's say, start at Unix timestamp. The second input is end at Unix timestamp, and you obviously want these two such that the second Unix timestamp, the end at, is higher than the first one. We have also example within our GitHub repository for Trident, which is really similar to this example I'm talking right now about. So you obviously would like to have the end at interval or the Unix timestamp higher than start at, so you can specify with this, for example, let's imagine that the input 1 is the start at and input 2 is end at, so you can specify with this macro something like input 1 would be from range, for example, 0 to 100, and the end at, as we can imagine, would be from 120, for example, to the 200. So, and then always the numbers from these two ranges are sent to the instructions. So this can be really helpful if you would like to set boundaries, limits to the instruction input parameters. For now, I can remove these macros, but you can find them, or not remove, I can comment them out, but you will find them within the materials on GitHub, within the example for this lesson. The next thing I would like to talk about, which is almost the last thing, is the custom error handler. which is also useful, but probably not that often used. And it is pretty similar to the invariant check. So in this case, the update instruction, which is common, has specified get data, get accounts. Then we have the additional invariant check, and you can also specify the custom error handler for the instruction. So if the instruction returns error, this method is invoked and you can perform checks on the error. In this case, I have prepared example where we actually unwrap the layers of the error that was returned from the instruction. So firstly it was Bank's error, then the instruction error, and so on and so on. For this important, you can find this within the Anchor GitHub repository, and they say that the custom errors specified or like this starts, or their error numbers starts from number 6000. In this case we have only one number, which is this variant is equaled to 0. So in this case the return or the error code would be 6000. You can use this handler, for example, if you would like to check that the instruction data sent in this case the input 2 was sent and the instruction behavior was as expected. In this case we check if the return error of error code 6000, which is basically the error we have specified here, invalid input number, when the instruction returns this error, if actually the instruction input data were higher or equal to 254. And if so, the fuzzing session will panic and we actually found an issue in this case. So again, let me remove the crash file. Let me close this debug window, clear the terminal, and let me double check. So I will comment out this invariant check so it won't trigger any issues, and I will double check if I have commented the well-structured data. Yes, and yes, so this is specified correctly. Let's now start fuzzing again. Fuzzing just started, and you can again see that we already found an issue. So let me just stop the fuzzing session and let me run the debug window again. Fuzz tests, fuzzing, workspace, and the crash file. Okay, so the output just loaded, and we can again scroll up, and you can see that there is the message. There is also the line where the panic occurred. So in this case 232, we can check that it is this line with the message expected error returned, which is basically the same as specified here. So, and we can double check. So for input 2, as we have specified in the update instruction, if the input 2 is higher or equal to magic number, in this case, which is correct, it will return the invalid input number error, what was actually checked with the custom error handler. You can use this custom error handler for multiple scenarios, checking let's say expected behavior. Even if the error is returned, you can return OK and just skip the error. You can use this instruction error handler within the instruction sequences. So if you expect that the instruction from the sequence will return error, let's say some instruction from the middle will return error, you can specify this instruction custom error handler that in that case the instruction returns error, just return OK and continue with the instruction sequence. This is everything important from the custom error handler. I think we went through all of the stuff from the fuzz instructions.rs, and the last thing I would like to talk briefly about is the Trident Manifest. So there are a lot of parameters that you can customize, that you can specify. For example, there are the directories, there are the there is the extension you can specify for the crash file, directories you can specify for the workspace, for the target directory, for the crash dir. You can specify the runtime. So for example, if you would like to, we can specify 10 seconds and start running. So you would see that it started on 10 seconds and it is counting down to 0 seconds, sorry. So the fuzzing session actually ran for 10 seconds. You can also specify save all, which will save all of the crash file, not only the unique ones. For the or about the statistics, I was already talking about this feature. You can turn it on or turn it off. Then the iterations are also pretty self-explanatory. This threads is I would say most of the time useful when you want to debug the fuzz tests, which I will show you right now. So you want to see, for example, if the fuzz tests are behaving as expected or what is actually happening during the fuzz tests. So in that case, you can, for example, specify iterations to 10. You can specify the threads to 1. That means every iteration of the fuzz test or the fuzzing session, we have specified 10 iterations. So every iteration is going to be processed sequentially, not in parallel as by default with the 0. And then you can specify these two options, keep output and verbose to true. And the results are such that everything is printed to the terminal, and you can see the Solana logs for every iteration. So if I scroll up, this is basically Solana. These are Solana logs for each iteration. So you can check what are the outputs of the 10 iterations during the fuzzing session. So we can see there is the anchor error returned because of asset account, which means there is account not initialized, so the account ID was different as it should, so this is the mismatch. What I found really important here also to mention that you can print a lot of important stuff, for example using the message macro in the Solana program that will be shown in the, or that would be shown in the Solana logs, or you can even specify let's say something like error print line XYZ, and this error print line XYZ would be printed in the also in this output. So you can use this to debug the fuzz tests. What is important is to specify the iterations to lower number, not thousands, because there would be Solana logs for all of the thousands instructions. So you need to specify some lower number, let's say 10, but it is also important to specify the threads to 1, not 2, 3, 4, 5, because it would start processing the iterations in parallel, and it would mix the Solana logs. So yeah, I think these are all of the features that I would like to show you in hands-on example. If you have any questions, as you already had in Discord, but if you have any other questions regarding these features, or regarding the documentation, regarding the Trident, even regarding the the architecture of Trident, like the underlying data and what is the arbitrary and so on, just feel free to ask on Discord, we can discuss. And yeah, this was all from the lesson 4 of the Solana Auditors Bootcamp. I would like to thank you for your attention, and I'm looking forward to the next lessons video. See you soon, guys.